Alright, so moving on to the next question, that is 1361 LeetCode, which is validate binary tree nodes. It has been marked as a medium level problem. So let us go over the problem statement first. So you have n binary tree nodes numbered from 0 to n minus 1, where node I has two children, left child I and right child of I. Return true if and only if all the given nodes form exactly one valid binary tree. All the nodes form exactly one valid binary tree. Okay, so if node I has no left child, then left child of I will be equal to -1. Similarly for right child, note that the nodes have no values, and that we only use the node numbers in this problem, right? So there are no node values, we only use the numbers that have been assigned, that is index. So left child and right child have been given to us, and for n equal to 4, so this is basically the indexing that has been done, 0 1 2 3. So basically 0 is the node that we have, right? From 0 we have left child as 1 and right child of 0 is 2. Similarly for node 1's left child, that is -1, and node 1's right child is also -1. So we basically have null. So basically this doesn't need to be there. I'm just showing you how we forming the tree. For node 2 the left child is 3. For node 2 the right child is -1, that is equal to null. Similarly for 3 it is -1 and -1, that is equal to null. So basically this is the graph that has been formed, that is 0 1 2 3, right? And now we need to validate it, whether it's a valid binary tree or not, right? Now this is the example. Another example, you see this is not a binary tree because this forms a graph. Okay, so here also we know that it is false, and this is also not a tree because there is two basically edges, that is the bidirectional edge. So we cannot have bidirectional edge. If in a binary tree, we have to make sure that we have at least one root, not at least we have one root, only a singular root, and each node should have a parent, right, except the root itself. And a node cannot have more than two children. It should have only a left child and a right child, right? And this can also not happen that we are sharing a node. So it cannot have two parents. It may have a parent and then a grandparent. So ancestors are allowed, but two parents of the same level cannot be allowed, right? So this is basically thought process that we have. Now let me show you the whole solution, how we're going to be tackling it. So basically a binary tree must have a root, as I told you. This is a node with no incoming edges, that is the root has no parent, right? So that is our first condition, that is if we have no root, then it would be an invalid binary tree. Every node has an incoming edge in this graph, right? So this is a graph. Now every node other than the root must have exactly one parent. Again, I've shared this. The red node has more than one parent. You can see that this is also the parent, since there's a directed edge from this node to this node, and root also, that is marked here, has a directed edge from this to red node. So it basically has more than one parent, so that is also invalid. Now the tree also must be connected, that is every node must be reachable from one node, the root. The nodes are disconnected, right? So in that case also we return false, and there cannot be a cycle, right? Invalid tree because there's a cycle. Now to solve this problem, we have to check the nodes against these given rules, right? For example, if a binary tree had a root, it would have a cycle only if it was not connected or there was a node with more than one parents. This is basically the rules that imply each other, right? So our first approach is basically our DFS. So if basically one way to solve it is that we check all the rules are followed using a DFS. So firstly we need to locate the root, right? We need to find the root that helps basically the function find root would help us find the root. So the input arrays left child and right child describe all the children, so the root would not appear in these arrays. We can simply use a for loop from 0 to n minus 1, and for each number check if it is present in left child or right child. If it is not present in either, then we can return it as the root, right? So the root would never come because the root has left child and right child, but it has no parent. It would not be a left child or a right child of any other node. So that means it won't be present in the left child and right child vectors, right? So basically this is our function find root unordered set int children, right? So we take children and insert our left whole array and the right vector as well, and we check if we are for all the nodes we are traversing, if we are not able to find it, that is children dot find of I is equal to n, that we have reached the end and still not able to find our node I in our unordered set, then we return I because this will be root. So we return the root, and in case this condition does not hold true, we return -1, that is there is no root, right? Now we will start by obtaining the root. If root is -1, there is no node without a parent, and we can immediately return false as the tree is invalid. Now once we have the root, we can start a DFS from it. We will implement DFS iteratively with a stack. How can we validate the tree? So first of all, if we see a node multiple times during the DFS, it means the node has multiple parents, right? And that could be a cycle. So we will use a set scene that keeps track of all the nodes that we have seen so far during the traversal. When we move to a child, if the child is already in scene, that means it has already been visited by another node. we can immediately return false since we would be visiting child for the second time. Now once the DFS finishes, every node we visited will be in scene. If the tree is connected, then the length of scene will be equal to n. If the scene's length is not equal to n, that means that some nodes were not visited and thus the tree must be disconnected. Thus we can return scene.length equal to n. That would check whether it is true or false at the end of the algo. So this process is sufficient in validating a binary tree. So these are the 4 conditions. That is, the binary tree does not have a root. If it does not have a root, then we basically return -1. If there's a node with more than one parent, then we detect it with scene. If the tree is disconnected, the scene length would have basically scene length would be a value less than or equal to n. Scenes dot size or length, whatever, will hold less than n nodes at the end. If there's a cycle, then we will detect it with scene. Any other scenario we don't explicitly check for will be called by some other rule, right? For example, the second rule we stated that every node other than the root must have exactly one parent. So basically, you must be thinking that we are explicitly checking the case when a node has multiple parents with scene. But what if there is a node with no parent other than the root? What if there is a node with no parent other than the root? That is, what if there are multiple roots? In that scenario, find root gives us the root with the lowest value. We would perform a DFS from there and never reach any of the other roots. Then at the end, scene would have less than n nodes. That means it is already a disconnected graph. So basically, it will be checked by all the other rules that we have stated here. That is the 4 rules. So our algorithm looks something like this: that we define find root, that gives us the root, then obtain root from find root. If root is -1, we return false. Initialize the stack and set scene with root in them. While the stack is not empty, pop the topmost element of the stack as the node, and iterate over the children of node given in left child of node and right child of node. For each child, if child is -1, then ignore it as that means that there is no child. If child is already in scene, we return false and push the child to the stack and add it to scene. After DFS, we return scene.length is equal to n. So basically, let me show you what I've done in my solution. So we have basically done the same thing to find the root, taking the left child and the right child vectors along with n. So on our set children, we insert both the left child and right child, all the values into our children set, and we go over all the nodes. We check if the node does not exist in the children set. That is, after traversing the whole children on our set, we have not been able to find the node I. It means that this node I has no parent. That is, it is the root, right? And otherwise, if we get out of this loop and we don't find any such root, we return -1. So we don't find a root. Now, first of all, if we see a node multiple times during BFS, it means a node has multiple parents and there could be a cycle. We will use a set scene that keeps track of all the nodes we have seen so far during the traversal. When we move to a child, if the child is already in scene, we can immediately return false since we would be visiting the child for the second time. This is repeated. I've already discussed it in our intuition and approach, right? So now let us get to our main function, that is bool validate binary tree nodes, which takes n and left child and right child. So root, find root, we get the root first. If root is -1, we return false because we don't have a root, right? No root. This is no root, right? So if we have no root, it is invalid. Then we maintain a set on our set of scene. So this will be storing all the nodes that we have already seen. Stack, we maintain stack of int type. Scene.insert root and stack.push root. While the stack is not empty, we extract the node from stack stop and pop it out, right? So in children is the vector in which we're storing the left child and the right child of that particular node, right? So node has left child and the right child. For each child in the children, that is, for each, we're traversing over each child. If the child is not equal to -1, that is, we do have these children. If we find it in our scene unordered set, if we do find it, scene.find child not equal to scene.10, that means we find it, we return false. That means we have multiple parents of cycle because it is already seen earlier, right? So this is the second time that we are seeing it, so we return false. And we we basically push it into our stack, the child, and insert it into our scene. And finally, we return scene.size equal to n to check if all nodes are visited.